exponential growth and decay. So whenever we see exponential functions, this is where they're applied. We talk about things that have exponential growth, for example, money or bacteria, and we talk about things that have exponential K, for example, carbon-14 when it comes to dating ancient artifacts. Our objective, we want to graph and apply exponential growth and decay functions. And give me a moment, I'm pulling out my Desmos in case I'm going to make use of it. Okay, so what do we know? We know what an exponential function is. Any function of the form f of x equals b to the x, where the base b is greater than 0 and not equal to 1, and the exponent x is any real number. Okay? So what is exponential growth or decay? When a value increases, growth, or decreases, decay, at a rate directly proportional. In other words, you're multiplying it by a factor to its current value. So we're multiplying by the same thing over and over again, and that or you could be dividing by, but of course division is multiplication by the reciprocal, by the same thing, and to get to get a new value. So very fast increases, again, that's growth, or decreases, that's decay. The growth example would be like doubling. You want to double your money, so you're multiplying it by 2 each time period. The decay example would be halving. In other words, when you divide by 2, it's the same thing as multiplying by 1/2. So there's your decay. Let's take a look at some examples of this, and we'll even do some application problems as well. So let me get my paper up here for you. Okay, as we know, get that straightened out. As we know, our world population is increasing. And it's increasing from a source that I got at approximately 1.1% per year. What this means is each year the world population is 1.1% more than what it was the previous year. Okay, so as the previous year gets higher and higher and higher, the 1.1% more, which means multiplied by 0.011, increases it faster and faster and faster. Okay, so here's the example that speaks to that. Let's take a look at the end of year 0 in 2020. Okay, so world population at the end of 2020 was 7.6 billion. So we're just going to focus on a number. We'll use the word billion to tell us that it's a really big number. So what happens at the end of year 1? Well, it grew by 1.1%. So we started here, and we add 0.011 times 7.6 billion to get to 7.684 billion. Okay, and then in year 2, we start here, and then we add 1.1% more of where we started from. Okay, now let's remind ourselves, we can rewrite this. This number is here, and this number is the same as this number. So I'm going to rewrite this as this. And you can see 0.011 times 0.011 times 7.6, and that gives us this 0.011 squared number, a number multiplied by itself, times 7.6, and here is the new population. Okay, it's grown a little bit more. And then we start again in year 3. We take this number and we add 1.1% of that starting number. Okay, this number we see is right here. Okay, we did this to get this, so I replaced this with this here. And notice I now have 3.011 factors. And I come up with this number. And then in year 4, I just noticed there's an exponent of 1 here. There's an exponent of 2 here. There's an exponent of 3 here. There's an exponent of 4 here to get to this number, so it is growing exponentially. And you can see that because the 0.011s are multiplying by themselves. That is exponential growth. Okay, let's take a look at a money example. Give me just a moment here. And I'm going to show you a little different, a slightly different way to look at how this growth takes place. Compound interest is the same idea. Okay, you add interest onto the new balance, add interest, get a new balance, etc. In that you earn interest on your interest, so your money grows faster. For example, deposit $10,000 into an account paying 5% as a decimal, 0.05, interest, and we're going to compound it annually, which means once per year. So we're starting at the end of year 0 or at the beginning with $10,000, and then at the end of year 1, we had our $10,000. We add 5% of $10,000, and now we have $10,500. This is now the beginning amount for the start of year 2. Here it is. And we're going to then take 5% of that amount during year 2, and we have this number. And that means we have an increase of 525. So notice from here to here, we increased by $25. And then we take this number at the start of year 3, and we put it here, and we then add 5% of that number, and we get to this number. And there's our increase, which is an increase again from here to here of 26.25. So you can see it's not a linear increase. It's not increasing by the same amount. It's increasing by more. And the next year 4, it'll increase by more than 26.25. It'll begin to increase faster and faster and faster as things go on. That's exponential growth. So here's the model for exponential growth. Took this right out of the book. What you're looking at here is my here's my base. There's my exponent. Okay, so we're looking at the same idea here, although we often include a number out front. And the K is the growth rate. So the base is still greater than 1. In an exponential growth model, the base is greater than 1. We need an A. Our A is positive. It's a starting number. And our K is going to be greater. It's going to be positive as well because that's growth. So K being positive is growth. Again, notice we saw this graph in a previous video lecture. There's the growth. We don't have any x-intercepts. Our y-intercept in this case crosses where 0a is located. Domain is still all real numbers. Range is all real numbers greater than 0. The horizontal asymptote, again, is the x-axis. And the shape is increasing and concave up. It's got a curve, and the bowl kind of points up. Here's the kicker to this, and we'll do some examples later on that work with this. The variable k is a constant. It represents the growth. Again, because it's positive, it's the growth rate. It's the percent. It's written as a decimal. Okay, and we know from our exponential rules, b to the k x is equal to b to the k to the x, because when you have this situation, you multiply your exponents to get to here. So your b to the k might be represented as a single number if we already know the growth rate, for example. We'll just kind of store that, and we'll see how that works with a couple of examples we'll do a decay example. But we might have this number, b to the k, be a number, be the base, and just have the x and the exponent like this is. Or we might have this be the base, we might have k, and we might have x be represented in our exponent. All right, let's take a look. Here we go. I just got to turn it over. My 2 growth examples here. All right. Oh, and I do have a graph I got to get ready. Okay, I thought about that. Let me get my graph ready. Example 1. Total personal income in the United States, and we're talking about billions of dollars, for selected years from 1960 and projected to 2030 can be modeled by this exponential growth function, y, okay, which is the total personal income. is equal to 492.4 times 1.07 to the x. Okay, so you'll notice here that my base, I don't have a growth factor k, it's incorporated into the base here. And x is the number of years after 1960. Letter A, what does the model predict that our U.S. personal income will be in 2014, or was in 2014? All right. Well, let's see. First, we need to know, let's first put an A. We need to realize that X is the number of years after 1960. So how many years is 2014 after 1960? And that is 54 years after 1960. Okay, so now we can use our model. Y is equal to 492.4 times 1.07 raised to the 54th power. And that can go into a calculator. And out comes, well, what comes out is 19012.6. And of course, this number is billions of dollars. So it's billion. We don't often write billion with this. We'll just make a note here. This is approximately 19 trillion. Move the decimal 3 to get to trillions, you got about approximately 19 trillion. But the model predicted the total U.S. personal income in 2014 would be a little over 19,000 billion. And 19,000 is the same as trillion. Letter B, graphically, determine the year which the model predicts that the total U.S. personal income will reach 28.5 trillion. Well, let's recognize that our model is in billions, so I wrote the number 28.5 trillion in billions so I can use our model. Okay, so we know we're looking for, let me write this down first. We know the income, which is the Y value. So our equation is going to be 28,500 is equal to 492.4 times 1.07 to the x. We don't know how to solve this for x yet. We're going to learn that in future lessons. But we can always solve these things graphically. So let's set y equal to the left side, 28,500, and let's set y equal to the right side, 492.4 times 1.07 raised to the x, and let's use a graph. So let me get my Desmos out here. Give me just a moment to, okay, there it is, okay. Let's get my graph out. Hope I got it straight for you. And we'll go into here, and my first one is the y equals the left side, 28,500. Wow, that's way up there. I gotta do some serious scaling to get to 28,500. There it is. I had to really scale my y-axis to get to there, but it's that green line here. And the left side is y equals 492.4, and then open parenthesis, 1.07 raised to the x, and then I'll come over and I'll close my parenthesis. And you can see that in the purple in my case, there's the exponential growth function taking place. And it looks like they're going to meet. I need to do a bit of, doing, there they go. There's my intersection point right there. And so what x value is that? That x value is 59.983. That's when the two have a y value of 28,500, which is what I want to have. So my answer is 59.983 years after 1960. Okay, so we'll go to here. We solve this graphically. And so it takes place when x equals 59.983, and we know that is years after 1960. So we're going to round this up because it's past the 59th year and we're into the 60th year. So 1960 plus 60. The model, let me go up here to the question. The model will predict that total U.S. personal income reaches this number in approximately, or it reached this number in approximately 2020. So we're able to solve this graphically, of course, with y equals the left side and y equals the right side, and then find the point of intersection. Example number 2. Okay. The future value, S, of an investment of P dollars invested for T years at an interest rate of R, expressed as a decimal, compounded annually, is given by this exponential growth function. It's exponential because you have a variable in the exponent. S is equal to P times the sum 1 plus R raised to T, which is the number of years. If you invest $1,000 today at 5% compounded annually, did I write on that? Nope, that's just me. How much will you have in 10 years? Okay, S is equal to, well, we invest $1,000 today, that's P. That's P. This is R, and this is T. So P times 1 plus R, the rate is 5%, but we need to write that as a decimal. So that's 0.05, and the time is 10 years. How much are you going to have? Well, that's not too hard. We'll put it into a calculator. And we come up with the number $1,628.89, rounded to the nearest penny, rounded to the 100th place here. So another example of an exponential function, in this case a financial function. We'll do a lot of looking at finance coming up. It's very popular with exponential growth. We'll look at finance examples coming up in future lessons. All right, let's take a look at decay. Exponential decay models briefly. Okay, so as we know, decay means we're going down from left to right. We start off by decreasing rather quickly, but the decrease goes slower and slower and slower. This is primarily, we're going to be primarily looking, I'm trying to think here, we're going to primarily our K is going to be less than 0 in general, so we're going to kind of focus on this first example, but it can be either. We notice that the x-intercept, because the x-axis is a horizontal asymptote, we don't have any x-intercepts. We know the y-intercept is the same, 0, a. And domain, all real numbers. The range is always positive. We're always going to have positive outputs. And we're decreasing, and we're still concave up. It still has a curve in which the curve is kind of pointing upwards. Okay, let's again focus on that variable K. It's a constant. It represents decay. And so usually the K will be negative. Okay, that will show us that we have a decay rate, so it'll be less than 0. And it's again always written as a decimal, and it includes a minus sign. If there's no minus sign, it's growth. It's a positive, so it's growth. If it has a minus sign, it's decay. And let's note again that sometimes the B to the K might be already known, and so you could have this as a single number where just your X is the exponent, or you could have the decay rate up there, which we're going to see in our example. Okay, so we'll take a look at that in one example. It pays to advertise, and it is often true that weekly sales will drop rapidly for many products after you end your campaign. Okay, so you do a sales campaign for 6 weeks, and then starting at the very beginning of the end of that, your sales for that item start to go down because it's no longer out in front of people. So this decline in sales is called sales decay. Suppose that the decay, I have a spelling error here. Suppose that the decay in sales of a product is given by the sales equals 1,000 times 2 raised to the negative 0.5x dollars. Now notice here, this is an example where I have it here. I know that this is the decay rate. Okay, this is the decay rate. It turns out that this problem has the number in front of the x and the exponent. It's a decay rate because it's a negative, and 0.5 is 50%. So it's a 50% decay. Negative point. So it's going down quickly. Okay, X is the number of weeks after the end of a sales campaign, and S is the total sales of the product. Let's use this function to answer the following A, B, C, and D. What is the level of sales when the campaign ends? Well, when the campaign ends, the number of weeks after the campaign is 0. It just ended. You haven't had any weeks go by yet. So this means X is 0. Okay, so letter A, S is equal to 1,000 times 2 to the negative 0.5 times 0. Okay, into a calculator that goes, and out comes $1,000. So right at the end of the campaign, the level of sales is $1,000. What is the level of sales 1 week after the campaign ends? Well, X is the number of weeks after it ends. So in this case, X is 1. And we know from up here, it's going to drop. All right, it's going to drop fairly precipitously early on. Okay, so let's find out how much it drops from the X equals 0 from letter A. So S is equal to 1,000 times 2 to the negative 0.5 times 1. Into a calculator that goes, and the sales dropped to $707.11. That's a rather significant drop after 1 week. And we stopped advertising and sales went down pretty quickly. Letter C, use the graph to estimate the week in which sales equal $500. Okay, letter C. So we want to know our sales is 500, and we want to know what is X. So here's our, whoops, that's 1,000. Here is our equation, negative 0.5 times X. And we're going to use the graph. We haven't learned yet how to find the value of X in an exponent algebraically. So let's do a Y equals 500 and a Y equals 1,000 times 2 to the negative 0.5 times X. And let's see where that intersection point is. Okay, back to here. Let's get rid of this and get rid of that one. I'll press my home button, get back to my home screen, and this one says, okay, my left side is Y equals 500, and that's up here somewhere, so let's pinch this together. There it is. In my case, it's a black line. It's a black horizontal line there. And my right side is Y equals 1,000, open parenthesis, 2 raised to the negative 0.5x. And again, I'll come out and close my parenthesis. And my graph shows it pretty quickly. In this case, the right side, this exponential function is in red. And so there's my Y equals 500. Notice how the sales are declining precipitously, and then it starts to kind of level off. Okay, so we're going to touch that point there for intersection. And it says when X equals 2. When X equals 2, we've already dropped to $500. It only took 2 weeks. So let's make a note of that. Okay, it only took a couple weeks to drop to half. So this tells us when x equals 2. So 2 weeks after end of the sales campaign. It's already dropped to half. That was quick. All right, letter D. According to this model, will sales ever fall to 0? Well, let's go back to the graph. Okay, here's the graph. Okay, so this is the graph. I'm going to move kind of this way, and I'm going to really open up. Okay, according to this model, notice I'm changing my x-axis. I'm making my x-axis, my y-axis getting in closer and closer. According to this model, the sales will drop, but they'll never get to 0. The more I focus in on that, the more you'll see that there's always going to be a gap. And as I continue to focus after 39 weeks, after 40 weeks, there's 41.6 weeks. It's never going to touch the x-axis because that's how an exponential function works. So according to the model, it's never going to touch to 0. Okay, never. Now that doesn't really make a ton of sense in real life. Sales will probably come to 0 at some point, but according to the model, no. Sales will never fall to 0 because the x-axis is a horizontal asymptote. So there you have it, a little look at exponential growth and decay.